Ladies and gentlemen, welcome to Engineering Dynamics. In this video, we will be again looking at the linearization of system and the equilibrium positions, if they are stable or not. So let's jump right in. This is a video where we do not derive the steps that we do, we just follow them. So if you already know what to do, follow along. If you don't know what to do, please look at the derivation videos, that is 3 videos ago. Let's jump right in. So we have a system of a mass that is not attached to a normal pendulum, but just a spring and a non-conservative force. So in our case, we have 2 degrees of freedom, that is S and alpha. So this is our Q's, and we are already given the equations of motion. For now, we assume that Q non-conservative is 0, so that this force is 0. First step is to find the equilibrium position. So we set our Q double dots and Q dots to 0. So we get rid of this part, this part, this part, this part, and we are left with the first equations. We have this one, and for the second equation, we are left with that one. So if we look at the alpha first, we get 2 options, either 0 or pi. So again, it's the pendulum that is from top to bottom or upside down. Then if we use alpha 0 in the first equation that we got, we see that S is mg divided by c plus S0, or if it's alpha is pi, so if we're upside down, we have the length minus mg divided by c. So one time it's longer because we're hanging upside down, and one time it's shorter because the mass is compressing the spring. But there's another option, and that is that S is 0, so the spring is completely reduced to 0. And if that is so, we have again the first equation, where S in this case here is 0, and we do a derivation, a simple reduction of those terms to get cosine alpha is minus c times S0 divided by mg. And if we just want the alpha, we have to do a cosine to the power of -1 to get the angle. But the problem is that this only works if c times S0 divided by mg is smaller than 1. Otherwise, this is not possible, and this is not an equilibrium position. So now we have 3 possible equilibrium positions, but now we will be focusing only around this one, where alpha is 0 and S is this part. So again, we have here our equations of motion, and now we do the partial derivatives to get the M, K, and D matrix. For the M matrix, we have to look at the Q dots, so we have a M here and ms squared there. So this is all we need. In the first equation, we have a S, and in the second equation, we have a alpha double dot. For the K matrix, we have to look where we have a Q dot. We have one right there and one right here, but if we derive them partially, there's still one left. So in this case, we have a alpha left, or an S, or alpha dot left, and those will be set to 0 at equilibrium, and this is why we have 0 for the D matrix. Then for K, we do the same thing, but we only look at the terms that have a Q. So that would be this case, and this term and that term, and this term. So here we have, if we just look at the, what our coordinates were S and alpha. So if we just look at the S, in this part we have a C, we have no S here. The alpha will be to 0, so this will be 0. Then we have a alpha right there. Cosine of 0 is 1, so we have mg. Oh, sorry, we have, this is a 0, because if we derive it once, we have a sine, and a sine is 0. And here we have a sine that will be a cosine, and that the cosine of 0 is 1, so we're left with mg s equilibrium. If we now just look at the eigenvalues of K, because we do not have a D matrix, we already see that the system is stable because the eigenvalues of K are positive or 0. If we have a non-conservative matrix, a non-conservative force now, K will be different because we have a S here and alpha right there. Here we have an S, there we have an S, and here we have a S as well, and even a S equilibrium. So to do that, we already see that the M matrix will not change because this is not dependent on Q double dot, and the D matrix will also not change because this is not dependent on Q dot. So the only change we see is in the stiffness matrix, and now we can see how this K matrix, so the new stiffness matrix, can affect our system. I hope this video gave you a small introduction on how to work with those linearized system, or how to get those linearized system, and how non-conservative forces can affect different matrices. If you have any questions, feel free to ask them in the comments down below, and I appreciate your attention and see you next time.